All right, let's go ahead and look through some of the information necessary to complete this 3C lab on calorimetry. So, introduction section, like normal, gives you some key phrases and ideas, a collection of some of the units that are going to be important. In lecture, we use calories per gram degree Celsius, but these can be converted back and forth to each other. Then they give us a general idea of what specific heat means, and then you can slightly rearrange this formula to solve in terms of heat. So heat is represented by the letter Q. You can think of that as being like the quantity of heat, and then the Q makes potentially a little bit more sense. Now we have conservation of heat, which is related to conservation of energy and how these exchange and change temperatures. So we want to have a net zero change. Basically, that means that the heat lost from one object has got to be the same as the heat gained from another object, and eventually they reach equilibrium at some new temperature. Okay. Those formulas can be slightly expanded and then marked in accordance with what different type of fluid or object we're talking about. So if we want to find the heat from the water, then we need mass of water, specific heat of water, change in temperature of water. Similarly, for some fluid, we would have similar labels and track information there. This is helpful because we can mix fluids together, or in the case of down here, mix a fluid and a solid together and find some missing information. Now, because one temperature warms up and one temperature cools down, and the way that we move these around when we solve, we end up with a negative sign in this formula. Um, but a lot of times that's sort of absorbed, cancels out the negative that you might get from one of the temperatures dropping. So sometimes you'll take this minus sign and then reverse one of these where we've got final temperature minus initial. Sometimes you'll put initial first on just one of these and then use that to cancel the negative sign. We do that in lecture, but that wasn't done here. Not a big deal. Okay, so now we have a table of some values for specific heats. So some relatively common liquids, some relatively common solids, and some numbers listed out here. We will refer back to these later when we're trying to identify what some of our mystery materials are. Okay, so looking at our workspace and our general setup, a couple of things that we can see here. It's asking us in the first step to tare the scale. So T-A-R-E basically means to reset to zero. So notice that even though there's nothing on this scale, it's reading a small amount of mass. Sometimes these things get bumped, or if something on there was especially heavy, sometimes it'll press something slightly that has to be adjusted or reset, and that's what that button's meant to do. We can also kind of peek in the background for now, and we can see that room temperature must be 20 degrees Celsius because that's what's on the thermometer that's just laying there right now. Okay, so we are going to be asked a couple of questions here. As with other labs, make your best guesses, try to think through what you believe the answer should be. It does say select all of the following statements. So you can see that these are boxes and not circles. So typically there's multiple answers, usually two, could be three, could maybe be all of them, but not for this one. But give it a try. If you missed the question, read the hint, try it again. Normally those hints are pretty good at telling you what you need so that you can make a guess and get it right. Another question, similar rules. Try it, read the hint. If you don't get it right, try it again, and then hopefully you should get it. All right, so if we tare the scale, then that's going to reset this back to zero, so that's been done now. Then now we want to find the mass of just the beaker. So there's nothing, or not supposed to be anything in this. In the picture, yeah, they might actually, I don't know, it's supposed to be empty right now. There's kind of a weird shadow in there, it makes me suspicious, but we're pretending it's an empty beaker. And that means just the glass here, excuse me, is 61.2 grams. That's going to be important because, again, that was supposed to be empty. See, look, magically it's empty again. That's gone. So yeah, all right, they used the wrong picture, unfortunately. But we're going to fill that up in a minute, and we're going to use that to figure out how much water we get. For hopefully obvious reasons, we can't put water directly on the scale and find the mass. It would spill everywhere. But if we can find the mass of the container, then find the mass of them combined, and we can subtract and find the difference. This thermometer has been put in the water sample. If all of this has been sitting out at room temperature, then it all equalized to the same temperature. So there's the 20 degrees Celsius that we were able to peek and see earlier. Okay, so now if we take some of that water, notice that this level has been depleted. It was up here earlier and now it's down fairly low. And we fill up this beaker to a certain point, then the mass has gone up considerably. And we need to remember that this isn't just the water, this is the water and the glass. So the difference there will tell us what the water is. Okay, then we're going to do the same thing again. So notice that the water level's back up again. But this time we're going to heat up the water sample and we're going to see how things have changed. So we take it, we activate the hot plate, we put the thermometer in, and it increases for a while and it gets to 50. So keep in mind that it used to be at 20, now it's at 50, so this is a fair bit warmer. We're going to fill up our beaker and then transfer the beaker over to the balance and then find a new mass. Notice, and this is going to be important, the mass is actually slightly lower than it was last time, and it's, I think, exactly the same picture, but it's at least at the same water level that we had before. Okay, so then we will discard that water, we will refill the flask, we'll heat it up again, this time to 80, so another 30 degrees Celsius increase. Then we're going to fill up our beaker, and we're going to find the mass of that sample, which again you should notice is an even smaller number. So that should correspond with some of those short answer questions, or rather multiple choice question that you answered earlier. So we can use that though, and we can eventually find the density for each of these samples. What's going to happen, they were all measured out to 200 milliliters. We were recording our mass and the water and the beaker together. The mass of the empty beaker on its own was 61.2, again, regardless of the slightly suspicious picture. And so if we take each of these minus 61.2, then that's going to give us the mass of just the water. Then what you want to remember is that once you have all these values for the water, the grams per milliliter, those units give us a clue. Density, sometimes lowercase d, sometimes uppercase d, or sometimes a Greek letter rho, but density is mass divided by volume. If you kind of squint a little, the M and the V sort of look like a heart. So there's a memory trick for that formula. But that means that we're going to take each of these masses and then we're going to divide by 200 milliliters because they all had the same volume. And then that's going to give us our densities for each of these. One way to kind of think about this is that as the temperature increases, the water molecules have more energy and are moving around more, and so it's harder for them to stay closer to each other. And so they end up becoming more spread around, which means they end up becoming less dense. Okay, but there we go. For the rest of this lab, we're going to end up using the hot water. So we have some information there. We know the mass of the hot water. We know the density of the hot water. They also go ahead and tell us a specific heat for the hot water. For colder water, that number goes very slightly over 4. But for this much warmer water, it's a smaller value. Okay, so now we're going to try to find the specific heat for an unknown fluid. So notice that we've got, well, I guess we will have eventually a water sample again, but right now we've got this green sample of a fluid. No idea what that is. So hopefully through finding some values, we can go and calculate. All right, so we had a water sample, we filled up a beaker, we're warming the beaker. It says 80 degrees Celsius, which if we zoom in, we can see a little bit better. So we've got this hot water that we measured out and learned about in the first phase. That's going to get poured in the calorimeter, which is just basically a fancy, well-insulated vessel, usually with some access points for either stirring or finding temperature. Okay, but that hot water is going to be poured in there. And then we want to take the mystery liquid and we want to pour a sample of that, and we're going to heat it to 50 degrees here. Okay, so we want these at different temperatures so that we can see how they change temperature and what they get to, and then we can calculate a bit from there. So that full sample was heated up. It's poured into this cup, or rather into the speaker, which is put on the balance, and we find the mass. Notice that this mass is quite a bit more than what we had for any of the samples of water. So this is definitely not water. I would hope the green color would indicate that, but if it didn't, then this mass should definitely tell you. Okay, now that's going to be poured into the calorimeter, and then we're going to see what the temperature gets to at the end. So you want to remember that the green sample was at 50 degrees Celsius, and the water sample was at 80 degrees Celsius. And they use consistent decimal places though. And so this one went up to 60, and this temperature came down to 60 something. And so, they didn't change by even amounts. And that's once more what we're going to be able to use to find the specific heats. Okay, so to do this calculation, you want to remember that we have the mass of the water, the specific heat of the water, and the change in temperature of the water as values on the top. And then on the bottom, we had the mass of the fluid, so F for fluid because we don't know what it is, and the change in temperature of the fluid. You might be wondering, well, where's C for specific heat? But remember, that's the thing that we're solving for. So there's your CF. Okay, so several of these things we know and we can figure out. So the mass of the water we're going to use, because it was the 80-degree sample, we're going to assume that it's the same number or very, very close. Then the specific heat of the water was given to us here for an 80-degree sample. Oops, got my decimal place off the spot though. 3.873. The units here are designed to cancel with everything else, so that's going to be fine. In fact, in this case, it ends up being what's left over, and all the other pieces cancel. So we don't have to worry about units so much here. Then we want to find the temperature change. So remember that the water started at 80. It went from 80 down to 67.8. So that's a temperature difference of what, 12.2? Now, technically it's negative because the temperature dropped, but that negative would cancel with the one that should have been out front. So as I mentioned earlier, sometimes we reverse how that subtraction is done. So it just sort of eats the negative sign and we don't have as much work to do. All right, then on the bottom, the mass of the fluid. So we found the mass of the unknown fluid and the beaker together. Then we're going to assume that it's the same beaker, so we weren't given any different information. So we're going to subtract that away from what we had earlier. And we're going to have a remaining mass of 254.1 grams. And so technically what would happen is these grams would cancel those grams, so I've left them out. Then our change in temperature, we went from 50 up to 67.8. So that's a difference of 17.8 degrees Celsius. And then again, technically the degrees Celsius and degrees Celsius from here would cancel. And that's why our remaining units are that ugly combination of stuff. Okay, so to avoid some calculator issues, I would recommend that you multiply everything together on the top of this fraction, then multiply the things together from the bottom of the fraction, and then divide them at the end. If you want to do this all at once, you either need more parentheses in your calculator, or you need to multiply the things on the top and then one at a time separately divide each thing from the bottom. But that really boils down to calculator skills. Hopefully you're comfortable enough with your calculator that you can find a value for this. We end up getting 2.03, and if we back up and check our previous list, then 2.03 is closest to acetic acid, so 2.031. Now, acetic acid is technically vinegar, and it would normally be clear. So I think they just added some color to be confusing so that it wasn't immediately obvious, but that's okay. All right. Then we want to do it again. This time we have a red sample. We don't know what it is, and we're going to run through similar setup. So we had a water sample here that was filled to a certain point. It was now put in this beaker. This beaker is being heated on a hot plate. it is at 80 degrees Celsius. Now, because it's the same volume and same sample and same temperature, then we're going to assume some information about this water that we will use to calculate later. So that water, um, we will end up pouring into the calorimeter and calculate from there. Okay, so new question, true or false? So only two choices, give it your best shot. I want to give you a clue that Celsius and Kelvin have the same size of degree. They just have different starting points. So think about what that might mean. Pick your true or false guess. If you end up getting it wrong, well, read the hint, but there's only two choices, so it'll have to be the other one. But hopefully you get it right. All right, this one, you want to remember that joules are newtons times meters. It's one of our definitions for joules, and then newtons are a combination of things. Those are kilograms times meters per second squared. So think about that a bit. Think about what those pieces are and how they might combine or cancel, and that might give you your hint as to which one of these are actually equivalent to each other. So make your best guess. If you're not sure, read the hint and see, and then work on it until you get it right. All right, so back to this water sample. We've got it at 80 degrees. As I mentioned earlier, we are going to pour it into the calorimeter cup. Then we're going to heat up our unknown sample. So it's red this time because why not? And we're going to 50 degrees. So almost the same as what we did before, just looks red instead of green. Okay, so we're going to take some of that sample now that we've heated up the whole thing. We're going to fill up to 200 milliliters on the beaker. It's kind of small, but that's what that says. Then we're going to find the mass of it. So now this is quite a bit smaller mass than what the green fluid was. So now we know for sure that it's not the same stuff. We're going to take that, we're going to add it to the calorimeter, stick a thermometer at it, and see what it gets to. So once more, I want to point out this was at 50 degrees Celsius and then went to 68.8. This water, when we heated it, was at 80 degrees Celsius and dropped down to 68.8. If we look at our calculations again, similar steps to what we saw before. So the specific heat constant, so C, or specific heat capacity, C of the unknown fluid, so we'll put F. It's going to come from the mass of the water, which is going to be, we're going to use the same number from before. The specific heat of the water, which again is going to be the same number given to us before. Then the change in temperature of the water. So the water went from 80 down to 68.8, which is what, 11.2? And then technically, if you multiply all that up, it'll tell you the joules of heat lost by the water. Because of the way that we have conservation of energy, then that same amount of heat has to flow into our mystery liquid, and we can set this up. Also, technically, we're ignoring the negative sign on the change in temperature because we're canceling that with a negative sign that was in front of the original formula. Okay, so now for the unknown fluid, we've got 190.1 grams. That comes from taking the difference between the mass of the beaker that's filled up with the fluid minus what the beaker is on its own. Then we don't know the specific heat. Again, that's the thing that's out front here. And the change in temperature, this went from 50 up to 68.8. And so that difference is 18.8. If we run through and we calculate here, we get 2.36. And according to our list, if we were to go check it again, the closest one is ethylene glycol. All right. So once more, we want to do the same kind of thing. Notice we don't have a green or red vial this time, but we have a big metal block. So we can still do the same thing. And in fact, we can find the mass of this directly. We can apply heat to this directly. In some ways, this is actually easier to use. Okay, so water is heated up to 80 degrees, just like it has been for the other ones. That block is at room temperature, 20 degrees, because it was just sitting out. The mass is over here. We're going to pour in the hot water, and we're going to let them settle at some new temperature. So this picture doesn't allow us to see anything, but technically, we had the block here. This was at 20 degrees Celsius. from room temperature, and it got to 64.5. And then we had the hot water here. Look, there's a reason I became a scientist and not an artist, but we had our sample of water here that was at 80 degrees Celsius and came down to this temperature. Okay, so question here. Give it a try. It does say select all. So, and you see boxes again, typically is the clue for multiple choices. If you miss it, check the hint like always. Try it again until you get it right. And if we were to run our calculation from here, we would do the same kind of thing. So we're going to have the same mass of water. We're going to have the same specific heat of water. Our change in temperature of water is going to, remember we started at 80. So from 80 down to here. Then I'm leaving this one for you to set up. I'm not giving quite as much help here, but on the bottom of that fraction, you're going to have the mass of the object. Well, notice we don't have to subtract anything here because we didn't have a beaker and an extra thing. We were able to just stick that directly onto the balance and get a mass directly. But that's going to be there. Then the change in temperature, that's going to be 50 up to 64.5. And then there you go. If you end up getting a negative answer, then that means you didn't cancel with the negative that was in front of the formula, but the number should probably still be correct. Hopefully you get just under 3.5. And if we were to go look that up on our table again, which you can get to from either clicking the introduction button or in the live lab, you can click on specific heat lookup, and then you can match the closest one, and then it's lithium. And then that should be everything. So hopefully you've got everything answered. You've got a congratulations message. If you've missed anything, or if you submitted early, or if you ran out of time, then you'll have whatever your percent is that's complete here. But otherwise, that's it.